excuse me. How do you figure out if this thing generates anything? Maybe it generates something, maybe it doesn't generate anything. So one way to do it is to check which of these non-terminal symbols is useful and which ones aren't. Useful symbols are defined in the following way. They have to satisfy two criteria. Number one, there has to be a way for the symbol to generate a terminal string. It's got to be able to disappear if it ever appears in a sentential form. So there must be a way for it to generate a terminal string. That's one. And two, there's got to be a way for S to reach the symbol and create it in a sentential form. Now what we care about here is whether S is useful. We care about whether S has any way to generate a terminal string. And of course, S can get to itself in a sentential form. So it's only one side of this you have to do. So how do you check whether something generates a terminal string? You do an iterative process that's bottom up. You start with all the non-terminals that can generate terminal strings directly. And in Chomsky normal form, that's easy to do. You just go right through the grammar and check for all the single terminal productions. So how many of these SABC can generate terminal strings? Just B. And you put this in a little room by itself. And you come back later to send in more of its friends if it has any other friends. So now we go back to the grammar and we say, OK, I know that B can generate terminal strings. I want to see if there's other things that can generate terminal strings. So now I'm going to end up finding all the non-terminals that can generate terminal strings after two steps rather than after one step. And the way to do that is to look at all the productions on the right that have just terminal symbols in them, or terminal symbols combined with B's. Those are the only ways to get terminal strings. Either terminal strings directly or B's, because B's were the only way to get terminal strings in the initial step. So are there any productions that have just terminal things or B's? Not this, because that has C's and A's in it. It's got to be just B's and terminal strings. Just this one. So I add B to my list. Oh, it's already there.
Let's keep on going a few more steps.
Yeah. If I keep on going a few more steps, it just stays B. B is the only non-terminal in this grammar that can generate a terminal string. Not S, not A, not C. So this grammar doesn't generate anything, because S is the start symbol. So you can figure out if a grammar generates nothing by figuring out whether its start symbol is useful, whether it can generate a terminal string. Let me add one more thing and to see what this would look like if we did one more step. Let's say we put this terminal string in. Then we would start with B and C. And now we go through looking for productions that have B, C's, and terminals in them. Here's one, here, here, here. So it adds in S and A. Now if we did it again, it would stay S, A, B, C. It wouldn't stay. So you do this iteration until it stays the same. And you can't do it too many times, because even if you just add one non-terminal each time, the most iterations it's ever going to take is the number of non-terminals. Most it's going to take is 4 iterations. And each iteration runs through the productions once. So it's not a slow algorithm. It runs pretty fast. And it finds out whether any one of these non-terminals generates a terminal string. And if S is in that collection, then the grammar generates something. If S is not in that collection, then the grammar generates nothing. And that's the decision algorithm for finding out whether context-free languages are empty. It's the only thing you can do with context-free languages for the most part. Can't do much else.
Can't you look at the machine?
I don't know. I mean, I think you could, but I don't think it's as obvious. How would you look at a machine and decide if it accepts anything?
You just go to the start thing and see if you can get out of there.
But there might be a way to get out of there, and the stack doesn't let you get there. So you have to actually do some simulation. It's not quite that clear. I'm sure there is a way to look at the machine and do it, but I think not as easy to describe as this method. You'll see a lot of things at this level go back to the grammars. A lot of things at this level, don't work with the machines because the machines are harder to analyze. Let's do something else. Dimitri, you want to do something?
Just do. I mean,
What
what question did you answer?
I answered the question of whether a context-free language is empty.
Okay.
And that happened to answer the question of whether a deterministic context-free language equals everything. Because I can complement a deterministic context-free language and still keep a deterministic context-free language. And complementing it means that if its complement is empty, its original was everything. So if I can do this, I can solve that problem too. Donnie, you get it?
Mm-hmm. I just got lost in the transition there. But
Okay,
yeah.
but we're back. Okay. Teresa, what are you thinking about today?
I'll take any more hints.
Okay. I'm big on hints. I write the problems, I can give the hints. I write the songs.
About the 2B then. The ambiguity for given a CFG and a string Z in its language, does the string have two distinct derivation trees?
Let's talk about that. All together now. Alle zusammen.
Yes.
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 Fangen wir zu lernen an.
Très bien. Uff. Zut.
Für die Wissenschaft. Die wichtige Sprache zu lernen.
All right. Given a string x and CFL L, does x have two distinct derivation trees? I think this needs to be a grammar, not a language, right? Under G.
It has to be two or more than two, right?
Yeah. Yeah, at least two. So what does this mean, first of all? Remember, a derivation tree is also called a parse tree. It's a way of starting with a start symbol, going down this way to some production, and then ending it off with terminal symbols. That's the derivation of the string 1, 0 in this grammar. Okay? There isn't any other derivation of this string. Yeah, Dimitri. What?
I'm confused, Shai.
Tell me what?
Don't we have to check infinitely many derivations?
Maybe.
Finite number of derivations
Are there a finite number of derivations?
for a particular string.
We only need to find two,
Yeah.
and then we can stop.
And how do we know we found the second one? Or we haven't found there is no second one.
We certainly don't want to wander through an infinite collection of derivation trees looking for the two that are different.
But the CYK algorithm, for instance, would give us all of the derivation trees if we're careful about keeping track as we go.
That's true. It would. And that would be a pretty efficient algorithm. Let's not even care about being so efficient. Let's be even a little bit less careful and just see if we can do it at all. Because this is just a decision algorithm after all. And I agree with Chris is right. That implies there would be one. But let's think of just a more straightforward way of getting the answer whether there are two or not, regardless of how efficient it is. So what do we do? Dimitri asked the question, you didn't understand why we wouldn't have to look through an infinite number, but I don't think we're even at that point yet, right? I mean, did anybody have any idea of where we're going to go here? We got a grammar, we got a string. How do we come up with these derivation trees? And how do we know if there's going to be two different ones? How do we come up with any of them? Here, I'll put a grammar down. Here's a real one. Here. It's always good if you're not sure, just do a real example and torture yourself. There's a grammar. Chomsky normal form grammar. And I'm wondering, I'd love to know. No?
Because S appears in B.
Can't reuse S.
B goes to SB.
Oh, that's our book says that.
Okay.
That's okay. Not in my Chomsky normal form.
Chomsky say.
I don't think you care.
It's okay to do this. That's fine. That's no problem.
Okay.
Oh, I see. No problem. Perfectly okay.
I don't think he named it after himself.
Oh, he might have.
Why don't you just...
He didn't name normal after himself, that's for sure. I mean, this is a string. And I made it long enough so that nobody would have any idea at first glance whether it has any derivation, much less two derivations in this grammar. Okay, so you're a machine. You don't have to be clever. You're just a brute force machine, and you've got a million slaves you can make to do anything you want, and you decide you're going to make them do something really practical, like figure out whether this has a derivation tree or not instead of build a pyramid. All right, so they're all working on doing this for you. What are you going to tell them to do?
Try and build a string.
How? They're idiots. They don't know what to do. You got to give them a specific set of instructions. They have no idea what you're talking about. They don't even know what a grammar is. Give very specific instructions. What should they do?
Go to the first two characters, I guess.
You mean the AB?
Yeah, I was talking about from the string.
Yeah.
And then see what grammar, what productions you need to get that string.
Everybody go with that?
Well,
Yeah, I guess-
Neil
Yeah,
has a
good.
point. You can get rid of the AB right now because
Why? Because it's useless? All right. So I'm not gonna. There. Sorry. No more useless. I didn't mean for that useless symbol. It snuck in. All right, so Joe's idea, whether he said it in computer science terms or not, is to do this kind of bottom-up parse tree. Imagine that these are at the bottom of some tree, and he's going to work his way up, guessing which non-terminals these terminals replaced in the very last step. And he's going to do that by telling the person to try every single possibility. Right? The 1 could have come from a C, and that's it. So the 0 came from either an S, a B, or an A. So why don't we start with an S? And
If you get the 1 another way, you could stop. I mean, wouldn't that'd be two different ways of doing it? Would that be right?
no, we need to get this whole string. We have to work our way all the way back up to the top. So there's an S at the top, and all these productions coming out of that S whose leaves at the bottom look like this. And then we have to get another tree that looks completely different that has the same leaves. Then we're done.
But if one of the way, if I can get 1, I guess it's the same idea. You know, if I can get 1 in 2 different ways, I will get 1 like with C or with A.
Yeah.
I guess I would be pretty much done. I
No,
guess I will
no.
do the whole string, but I can prove. That will be a proof that I can get the same string in different ways.
No, because let's say the other way is with a B, and then as we keep going, we find out that we can't put these all together and come up with an S at the top.
Yeah, but imagine it was just like the A, for instance, that it doesn't change anything. Yeah, I understand what you're saying. If it's a combination of 2, but I mean, if it was just like a single choice, C just give you a 1 if you want.
If we only had a single string 1, let's just say that the string was just 1 for a second. Then you can start out with a C, right? And that's all. And now you can't do anything else. But this is not a derivation tree for 1 because a derivation tree has to start with an S on the top.
Right.
So let's say it was just a single 0. Then you can have either an S or a B or an A. Only one of them is actually a derivation tree, only the S one. And that gives us 1 derivation. The others don't give us another derivation. You get all that?
Yeah.
Okay. So I'm not even sure this is going to... I'm not sure. I mean, maybe I get an idea of how this might give us 1 derivation tree, but I don't see how we're going to use it to get 2, or maybe I do, but I'm not admitting I do. What do you think about this idea? This is a bottom-up idea. I mean, could you write a program to do this? I mean, what are we doing? Say I do guess S, C, and S. What do I do next? Want me to do this to all these guys? Get little capital letters up on top? We could. So now I got a whole bunch of capital letters up on top. What do I do next?
Is at that point, see how you have CS?
Yeah.
Can have it, CS can't come from any production.
That's right. It can't come from
Just
anywhere.
cross it out and
But
put a B
but
there.
you sure could, because you could have a CB. CB could go,
Well,
and the B could become an SB.
not to generate 2 characters though.
Yeah, you could. I mean, for that particular little bit,
The next-
say
the
that
row
zero,
above it
say that
could-
0 is, the next 0 goes to a B.
This one here goes to a B. And say that SB came from a B,
And that's
and this CB came from an S.
Okay.
It could be that. The point is, yeah, okay, there's a lot of things we have to try. How many are there? And I don't care to count the exact number, but is there a finite number or is there an infinite number?
There's a finite number.
And Dimitri said there's an infinite number.
Well, you just chose you got lucky there and chose something that's, where everything's finite. What if you have some epsilons around and, things that could loop? Maybe, what if you have a lot of epsilons around and things cancel out? So, you can have a really long derivation.
Epsilons do make it much more complicated because the tree can disappear as we're going up, but it's the Chomsky normal form, so that's why you have Chomsky normal form, to avoid all those issues. How long does it take? What's the worst? I don't know how to count it exactly from the bottom up, but I do know how to count it from the top down. And I think for the top down is a little more organized because I know the top's got to have an S on it. So why should I start from the bottom and just hope I can get to an S and working my way backwards? Why don't I just start from what I know it's got to start from? I know it's got to start from an S. And now I got two choices to continue, or the terminal string. So what's the maximum number of choices I have at any stage to substitute a non-terminal for? 2 or 3. And how big is the string that I'm going to end up doing? 3, 6, 9, 12, 15, 17 symbols. Right? So how many different trees could I possibly have to come up with a number of leaves that's equal to 17? What's the biggest amount of trees I could have?
2 to the 17 minus 1.
Yeah, something like that. Or if it's 3 choices, 3 to the 17 minus 1. I can just do them all. I can come up with all the possibilities. I can start with S going to choice number 1, S going to choice number 2. Here, this is not a parse tree. This diagram I'm going to draw now represents all the parse trees. Everybody see that? It represents all the parse trees. From AB, I can go to,
BC.
this one goes to
BCSB,
BC, SB, BC, blah, blah, blah. A lot of possibility. I can just go ahead and keep doing this. And sooner or later, I'll have enough non-terminals here to generate 17 symbols. It's going to be a finite number of levels before I have enough. And after that, I don't have to look any further. After that, any string I generate is going to be longer than this. So either I find 2 that are the same by just brute force trying them all, or I get strings that are too long, and I'm never going to find another one. If that isn't quite a good enough hint, let's think about how long it takes to get a string of 17 symbols in Chomsky normal form. How many steps?
2n minus 1.
2n minus 1. So 17, I thought?
17 times 2.
34.
34, sorry.
Wow. 33 steps. Just checking. Little check. Okay. 33 steps. So what do I got? I got 33 steps, and every step I have how many choices? 2 or 3? Right?
Maximum number of right-hand sides?
Right, the maximum number of right-hand sides. So worst case is 3 to the 33rd possible things I have to check. And after I'm done with that incredibly large number, either 2 of them are identical or 2 of them are not.
How does that relate to the, what did we say, 2 or 3 to the 17?
Because that one doesn't include
The final, the terminal?
the terminal ones, and you really do have to include them.
Because there's ambiguity.
Right, because there might be choices there too. So it really is 3 to the 33rd. It's really a lot.
And if we had 5 options or more, which Chomsky normal form doesn't limit that.
Right, but it's a constant number relative to the grammar. It's still finite. in any case. And you can definitely check it. So great. So you can check it, and you can always check for a given string whether it has two distinct derivations. Does that help you one bit to figure out if the grammar is ambiguous? No, because you'd have to do that for all the strings. And even if you started checking all the strings in parallel, like we started doing today, that dovetailing idea, so you try them all kind of at the same time, changing between one, and moving on one step with each one. So if there is one that will eventually have two distinct derivation trees, you will find it. In other words, it is possible, given a grammar, for you to find out whether it is ambiguous. That's undecidable, but it's at least partially decidable. You can answer yes when the answer is yes. But if I ask you whether the complement is true, whether it's unambiguous, that's not recursively enumerable. There's no way to have any chance to check that it's unambiguous.
This guy's fully decidable, so we don't even have to do the dovetailing thing.
This is fully decidable, right. This is just one single string, no dovetailing in this example, right.
But you have to start with the Chomsky movement.
It makes it much easier to describe and convince that you can get it done in finite time.
Otherwise, with the epsilons.
Right. With epsilons, you can't just go forward and say it's going to take 33 steps and then I'm done, and after that I don't have to try anymore. Because you can try, get some things that disappear, and then build up again. And it could be an infinite number of those. And in fact, you can build grammars that look like that. You want to avoid those grammars, and basically what you do to avoid them is to take the constructions that you get at the beginning, convert it to another grammar that doesn't have those issues, and you can actually take the infinite and turn it to finite. So yeah, Chomsky normal form is very useful for stuff like that. Yeah. All right, well, think about it. I'm sure you can probably find actually the solution to this in some textbook too. I mean, this is a pretty standard problem. You can probably just look it up if it's still not clear.
Is there a better solution than this?
Sure. Well, right. I mean, this is basically the flip side of the membership question. The membership question says, given a string, does this CFL generate it? When we figure out whether a CFL generates a string, we usually come up with a parse tree and say, yes, it does. Here's a parse tree. Right? And if it doesn't, we say there's no parse tree that could possibly work. So in the CYK algorithm, when we do that, if you remember the algorithms course, you can keep some extra information in those squares. And when you're all done, instead of just knowing whether the grammar generates that string or not, you actually know which productions help you generate it, because you remember which choice you took at each stage in order to put the non-terminal in the next square. And you can backtrack through those choices to get a list of productions. Now if you can do that, that information that you store along the way is actually enough to give you all the possible ways of getting that string, especially if there's more than one. And you can just have a little binary bit. The minute there's more than one way in that algorithm, you stop and say, this string has two different derivation trees. Basically, there's more than one way. Remember, I got to remind you what this was without getting into too much detail. Remember, like v15 depends on v11 and v24, and v12 and v33, etc. v13 and v42, v14 and v51, right? One of these has to combine. Say there's a B here and a C here, right? And A goes to BC. Then A gets put in here. So if there's going to be more than one pair that puts a particular non-terminal in this set, then that non-terminal has two different ways of generating that substring. If there's only one pair that does it, then it only has one way. So you can propagate that true and false value back and forth through. And that's a much nicer way to kind of do it because it's more efficient. You don't have to do it in this horrible exponential way. This is a prettier way. You have to be careful that we really don't care whether a particular non-terminal just generates something twice. We care whether the start symbol generates something twice. But you can just concentrate on that as you go along. So you need to talk about some details here, but you can fix it to work. Does it make a little sense? Do some more? Yes, Dimitri. Yes. Yeah, come on up.
I just wanted to,
Looks like he was on the phone.
I think we should, do some Turing machine stuff. Good day. What's that?
Oh, I don't think they want to.
Well, Joe doesn't want to, but I mean. Well, we'll do some other stuff. There's a couple other questions before then.
Did you already have practice for assignability stuff?
Well, yeah, that's what I wanted to do first. All right. So the first question is, oh, this is so clean. So let's say we have, this is number 13 from last handout.
I got new colored chalk, and I got this high quality amber chalk.
So we have PDA, a PDA-M, and a language 0, 1 star, 1, 1, 0, 0, 1. So, question. Star. Yeah, oh, that's right. Doesn't matter. But so let's say I ask the question, does this machine accept all strings in L? Accept every string in L. Is there a decision algorithm for this question? Every string and possibly more.
We must have done this in class, right?
That's a good review.
I don't know. I just don't remember if you did it.
Uh-huh. What's that? If I did this?
I'm trying to pretend I'm a student.
Oh.
No. Well, you have to figure it out. I'll just sit here.
Well, I have steps that would work if we knew that was a deterministic PDA. We know about intersectional.
But you can convert it to a deterministic PDA.
Not necessarily.
What is it? Okay, tell me what you would do if it was a deterministic PDA.
Take the complement and intersect it.
Take the complement and intersect it.
With that string.
It's not a string. That's
That
Finite state
language.
machine already uses that.
But L is a regular expression, and intersection is closed with regular expression.
We also know from our handout sheet that we can ask whether a regular is L equal to R.
Well, no, don't. Let's not look at the big table. You know, that gives everything away. But how do I do this? So the problem is, Joe wants to complement the M, but we don't know. We don't know about M, right? We don't know if it's deterministic or not. So what else could we do?
Well, the pieces look deterministic, don't they? Put in the 3 pieces.
No, wait. This is not deterministic. This is a non-deterministic push-down automaton.
We got two pieces. We have this non-deterministic push-down machine and a regular set. So one of the pieces is non-deterministic.
So you can't. I mean, you don't want to. So you're saying take the complement of this and then intersect?
What does that do?
Well, why would you do that? Yeah.
See if, and then you would see if it accepts any string with 0, 1, 1, 0, and if it does, then it's not the.
Well, how does that? I thought you. That just sounds like you're passing the buck. Instead of saying, okay, see if this string accepts anything like that, take the complement and see if that.
String in. And then if that one string is accepted.
So that's a little easier. It still seems like passing the buck, though.
No, because the intersection should come up with nothing.
Okay.
You know which string to pick.
Dimitri, did you make a picture of what it looks like?
All right, let's make a picture. Sure. What's your name again? All right. So. M. So M is some. We want to see if this is possible, if this is true, or if this is the case. If M accepts everything in there.
So M is the big circle?
Yeah, so like this is all of M. Sorry. And here's L. L is this thing. All right, so
So Joe wanted to take the complement of M.
Right, which would be the rest of the circle,
Right. And
intersect it with L, and pass in just any
See if
string
that's
with
the empty.
10110 in it, and if it comes out, if it accepts it, then you reject them.
the machine that would be the intersection of the complement of M and L would be the empty set.
Right.
Would generate the empty
Right.
The
set.
empty set when L is a subset of M.
Right.
right, and otherwise it wouldn't.
It would be something else if it wasn't.
Right, but we can complement M, so that would be
Right.
a good idea.
So you remove for the first case.
Well, would it be a good idea if we could complement M? That's what I'm trying to understand. If you can complement M, then you take the intersection of the complement of M with L, and if that accepts nothing, then we know L was a subset. And if that accepts something, then we know it wasn't a subset. So we don't have to throw in any string with 110 in it. We can just throw in any string and see if it gets accepted or not.
Right.
And if it does, then we say L is not a subset. And if it doesn't, then we say L is a subset.
You know your stuff.
I'm just clarifying. Make sure I get it.
All right. But we can't complement
But we can't
M.
complement it, so that's too bad.
Well, we can convert the regular expression to a finite state machine. Take that's complement and intersect it, maybe. Can you do that?
Well,
No.
but L is
No,
contained
because
in M.
there's
not
an
the other way around.
asymmetry. You need to
Right.
check whether L is a subset of M, not whether M is a subset of L.
Oh. Ooh, now I'm confused. Maybe you can't do this. I don't know.
You can't convert a non-deterministic to a deterministic machine?
No.
You want to know the answer?
Well, first of all, what if we just said if it accepts some string in this language? Could we do that?
We're just trying to come up with.
All right, so that's
If you asked it the other way, then Joe's method works. If you wanted to know whether the non-deterministic machine was contained in that regular expression, then you could do what Joe said. Right? You could do the same trick.
so. What if we said?
Complementing would be done on the finite state machine.
So we have this non-deterministic PDA-M. Does it accept some string in 0 or 1 star? What about that?
Now you're talking. Now you're talking.
Right.
I can do that.
Yeah.
Oh, I lost my footrest.
So how would I do that? Well, see, we have two people who claim to be able to do it.
I've heard
Anyone
you
else?
claim that problem is hard.
Maybe.
Undecidable hard or just difficult?
That problem, if Dimitri provides an arbitrary regular expression, not a particular one, but just says, is an arbitrary regular expression, a subset of a push-down machine? That's an undecidable question. Because if he could decide anything like that for any regular expression, then I'd just give him the regular expression sigma star. And I'd say, is sigma star contained in this machine? And he would tell me yes or no. And if he tells me yes, then I know that that non-deterministic machine accepts everything. And if he tells me no, then I know that it doesn't accept everything. So then I can decide whether a non-deterministic machine accepts sigma star. And that's not decidable. So there's no way that you can do that for an arbitrary regular set, right? He's just rubbing his chin. But what about this? This looks like it's easier. But anyway, you might be able to do that for that particular regular expression. I don't know.
Yeah, I don't know
It's
about
not
that.
for an arbitrary
No.
problem. In fact, an extra credit problem that I gave you on the homework asks exactly that question, but for the regular expression 1 star. In other words, does the non-deterministic push-down machine accept all strings with 1s in them? And that is decidable, even though you can't do it for a general regular expression.
So what about this one? What's the big difference? Somebody who's quiet.
Because you're not going to do the complement now, right?
Well, calm down. I know you know it. How do you do this one?
Oh yeah, isn't it in line?
Seems very similar, right?
Let me do it.
But
Let me do it.
no. So it turns out we can't do this. We can't do this in general for any regular expression for the reason that Shai pointed out. Because then I could test to see if this thing accepts everything. And we know we can't do that. But this thing, so different. It's just all becomes sum. And now what? Well, we can test for one thing. So how do we do that? So we're divided here. So we have 3 people who say yes. Anyone else? I want a quorum. I want a quorum of people. What kind of things can we do? We're talking about these. We have some ideas on the table. I think some of them might be useful. What could we do? Joe, you had some idea. I think you had some stuff that might work. Some variant of what you were saying.
What, turning into a finite state machine?
Turning this into a machine?
Yeah, or a grammar, actually, is what I was starting to think. But I'm trying to
Well, one thing's a machine already.
Right. So, can you intersect a DPA and a finite state machine?
Yeah.
Okay, so, well, it could be, a finite state machine is another, it can be a push-down automaton trivially, right?
Right.
You just don't do anything to the stack,
Okay.
right? Okay, so what do
The
you,
fact that you don't do anything in the stack makes it able to.
well, yeah, well, hold on, yeah. That's a very useful fact, in fact. But so turn it into, turn this thing into a push-down automaton. Or I guess we should say a finite state machine, just to be clear. Then what? What would you do?
Then it take the complement intersect it?
I don't think we
Or
need
I
to
guess you could union it. No, it has to be.
just
Why are you taking the complement now? Now we want to decide if there's any intersection at all. Right? We want to see if there's anything in common. So the 2 cases would be something like this. This would be no, and this would be yes. So what could we do? Intersection, yeah.
Right.
So why can we do this now?
Because if it accepts a string, after you intersect it.
No, why can we take the intersection?
Intersection is closed with regular language.
Yeah, it doesn't, the other machine doesn't have a stack. And then what?
Convert to grammar that comes into
And then?
check if S is useful.
Check if S is useful, useless, which we can do. Okay. So slight variations in the question can produce wildly different answers. So this might be possible in this particular case, but it's not possible in general. All right. Here's a random question. Nothing to do with this. What if I use a queue instead of a stack for my push-down automata? So it wouldn't be a push-down automata anymore. But what if I used a queue? What's that? A Turing machine. How come?
A queue can simulate the infinite. A queue of infinite size can simulate the ribbon just as well as.
Did you guys talk about this already in class? No. You just, okay. So how could you simulate an infinite tape with a queue? How do you move?
Positions and just, writing it that way.
What's that mean? How do I move right with a queue? I have some information on a tape. How do I move right?
You can only move right, but you can always pull something off and throw it onto the end.
Right, and how do I move left?
Well, you could have two portions of the queue. One would be the right half, and one.
Well, how does a queue work anyway? So a queue is this thing where you can put stuff in here, and you can take it off of here, and this can be as long as I want, right? Yeah. So how do I simulate? So how do I simulate moving? One way should be easy to simulate, right? Moving.
Right.
We need to have symbols to.
How do I move here? Let's say I can look at this, but then I just want to look at this. I don't want to get rid of this information. Let's say I want to look at this thing, and I want to keep these, and I want to look at that. How do I do it?
You have to cycle through the queue. Do lots of cycles.
Yeah. So you can put some sort of marker. So like some boundary marker, and then I could just put those here and keep on going around. So a queue can simulate an infinite tape. It can move left and right because we can move around. Cool. Trivial, right? All right. So why don't you design a Turing machine? I got a really easy one for you. Number 15 says a machine that takes input strings containing zeros and ones, rejects any input string that's not of length equal to 1, and it accepts otherwise. That's our baby Turing machine. So it's in the handout. So it rejects everything that's not any string that's not length equal to 1, and accepts all strings of length equal to 1. So something doesn't really need the power of a Turing machine. But if it's trivial, keep on going. So it's a 3-part exercise. Well, there's 4 of them here. This one is a 3-part exercise that copies, to build something that copies, in stages. Just wanted you to warm up to it. And if you're bored with that, you can build a machine that squares. You did that one today? Oh, I gotta talk to Sean about this. We can build a machine that cubes. What's that? And I guess we'll end stuff there.